This is Path Analysis Part 2, and I want you to actually start by pausing the video, going to reflection number 2 in the reflection guide, and thinking about how do we actually establish causation. So if we want to say this causes this, how do we do that? So pause, look at that. Okay, now that you're back with me, we just reviewed correlation versus causation. And so we can't say that a correlation is on automatic causation ever. In fact, it might be one of those weird ones. And in statistics, causal modeling doesn't actually prove anything either. Even with the fancy SEMs, even with a really well-designed study, we're just providing evidence for or against something that we are seeing. And remember that it takes 3 things to establish causation. Number 1, that the relationships exist. Number 2, temporal precedence, that A comes before B. Every time A comes before B. And then isolation, nothing else interferes with that line between A and B. That's extremely hard, and in social sciences, let's face it, it's pretty much impossible to get into a controlled setting where you can control everything else to really isolate. That tends to be done more in the medical sciences, where they do these crazy, crazy lab experiments where they try to control for everything. We don't have lab settings. We have real life settings, which are messy. So we don't tend to talk a lot about causation, true causation. We talk more about correlation and the patterns and the implications that we're seeing and kind of the flow of effects, but we don't really use the strong word, this causes this. And also, you don't do any of that in a single study. It takes years and years and years. But we are talking about causal modeling, which is where this gets a little bit confusing. So a lot of times, especially with practitioners, you show them these cool models and they automatically assume that it's causation. So check yourself when you're writing and explaining things. But we are talking about causal modeling. So there's actually causal relationships and non-causal relationships in a single model. This is where that importance of theory comes in. You don't just draw a picture where you don't have strong evidence and backing and theory of why you're connecting this to this, why this variable is important in this model. And path analysis actually estimates both. So it's going to estimate the lines that you create and the lines that could exist that you didn't, just because of the way that the matrices work. You think about one side of a Rubik's Cube, and you're looking at that side, but there's all these other sides and influencing things that are happening within that one cube, which is really what we're creating within these matrices. We're creating these 3D crazy things. So we can have causal pathways, which you draw. So X to Y. Why did you put X to Y? Why not Y to X? You have to decide all of that. We could also look at some mediation effects, so X to Y to Z. There's also times where models will have feedback loops. So X predicts Y and Y predicts X at the same time, or a larger loop. So X predicts Y, predicts Z, which comes back around to predict X. Feedback loops are extremely difficult to model, to get to run, to get the matrices to converge. You tend to have large samples, and it can be really convoluted in your findings. So I don't recommend feedback loops unless you absolutely need them. So these non-causal pathways are a little bit confusing because we're modeling them, but we're not really modeling them. They're kind of in the behind the scenes. So they can be between exogenous variables. They can also be between error terms. We don't talk about those as kind of causes. This error causes this error. So here's the simplest way to think about it. If this is our model, here's a whole pathway that's not being modeled. That would be a non-causal path. That the potential is there to draw the arrow, but we're not, and we're intentionally not for some reason. So recursive models are the ones that we're going to be doing, and they're just easier to estimate and they're more widely used, and they're the ones that don't have feedback. So the big difference between these two is right here. Our dependent variable is this 1x, and y is predicting this, this is predicting this. Over here, we actually have the recursive thing right here, that y is predicting x, and x is in turn predicting y. It takes a lot more assumptions, it takes a lot more theory to support it, and you need some more sophisticated estimates. Identifying these models can also be really challenging. So again, just don't do a feedback loop if you don't have to. So let's do a quick example and look at a simple path analysis and how this works. So here's our model, and if we were going to write that as a regression, it would look like this. So we have three things that are predicting motivation. If we were writing the equation, it would look like that plus residual. What path analysis does is we model the residual differently for each one, which is really cool. And it's just so much more easy. Also, all of these correlations and covariances that are right here between these guys help us account for collinearity issues. So if you have a regression model that just has a bunch of collinearity that you're seeing, putting it into a path analysis can help account for a lot of that. All right, so this is what it looks like when you model. So we have our covariances over here. We have error terms for each of these. But what we're really interested in are these guys right here. So these are sort of like the factor loadings that we talked about with CFA, but now they become the beta values for our regression. So if you think back to regression, we looked at beta values, which was like the impact that we could say that variable had on the dependent variable. That's what these path loadings are. They're standardized path loadings. So we can see really quickly that this one is almost 0. So extrinsic motivation doesn't predict holistic motivation hardly at all. Like there's no relationship there. Intrinsic does seem to have a 0.23, assuming that that is significant. We're at least having some sort of an impact on motivation. And agency would be the same thing. So agency has the most impact to motivation, but when we think about standardized loadings, those are pretty small. So they might both be significant, but we're not seeming to be explaining a lot of motivation. They're pretty low. In motivation, we will have an error term right there. And if you take that minus 1, that actually becomes our R squared. So that confirms what we were seeing here, that these are really small standardized loading, so really small kind of like beta values. Probably not explaining a lot, but they could significantly be explaining our R squared, which would be 17% of the variance. When we get into latent regression, which is our SEM models, we would be taking the exact same thing, except now agency would be modeled as a latent variable with lots of items attached to them, which are not shown here. And it's the same idea, but we are now going into latent regression or structural equation modeling instead of a path analysis.